My name is Jacob Barandes. I'm the co-director of graduate studies for the Department of Physics at Harvard, teach physics courses and philosophy courses, and I spend my time thinking about questions at the intersection of those two fields.
Yeah, and what if you are the first to unify quantum mechanics and classical physics?
As with all projects in science and certainly in philosophy, things are provisional, tentative, and it will take some time before we know whether these things really work in all their details. And so one question you might ask is, well, an algorithm in a computer, or a machine learning model, you're talking about processing information in some sense, arriving at conclusions, taking in some initial information in, processing it, arriving at some kind of conclusions about it. And there's a view that maybe physics involves the processing of information. And one thing I just wanted to comment on, because this comes up a lot, occasionally people will ask, maybe what is at the bottom of reality is just processing of information and that's it. Maybe information is all that fundamentally exists. There's this slogan, there are a lot of slogans in physics, called "it from bit," that goes back to an article, a lecture actually, from John Wheeler. I'm mentioning John Wheeler again. That was the thesis supervisor to Hugh Everett and Richard Feynman and Jacob Bekenstein and lots of other people that people have probably heard of. Ben Schumacher, who co-invented the qubit in 1992, he was their PhD advisor. John Wheeler gave this very interesting lecture in which he, introduced this slogan, "it from bit." His argument was that maybe all that there really was in nature was information, yes/no questions, or answers to yes/no questions, and somehow all of physics, all of nature was supposed to be emergent from this kind of a thing. That we live in a so-called participatory universe where everything is generated somehow by our interrogation of the universe through yes or no questions, and information is at the bottom of everything. I have to say that I'm a little skeptical of this view, whether you're talking about information in a quantum system or information on a computer. There is in all these circumstances a physical substrate out of which the pattern or information is manifested. So on a computer, you have physical hardware components. You've got some physical thing that is flipping from 0 to 1 or vice versa. And the patterns of zeros and ones are embodied in some physical object. The information can be abstracted away, and you can talk about algorithms and write down algorithms for various purposes that don't need to mention the physical thing realizing those patterns. But at the end of the day, if you want to actually implement this on a computer, you need hardware. There must be hardware to actually realize the patterns.
I do want to kind of slowly build up to it, and we'll do like a better sort of finale towards the end. But it's also really important, I think, that right away people understand that you have done something pretty interesting. Like you've rethought the way the wave function is thought about and conceptualized into something that's more of a classical stochastic process. And for some reason, when I late at night heard this idea and listened to your podcast, I could not stop thinking about it. And I was just dying to dive in more. So maybe you could just explain what inspired you to bridge that gap between classical stochastic processes and quantum mechanics.
Yeah, thanks. So, just to get off the bat, there is a certain kind of paradigm, a framework that people who work in physics, in quantum mechanics in particular, often take. It's a framework that newcomers to the subject often see when they first show up in their first class in quantum mechanics. And this paradigm is that quantum mechanics is first and foremost a story about wave functions. Wave functions are the primary character, they're the protagonist of the story of quantum mechanics. And that the thing to do in studying quantum mechanics is to figure out what the wave function is, how to use it, what role it plays, and to make up your mind about what your view is on the wave function physically and metaphysically. And so people will debate, are you someone who thinks that wave functions represent something physical out in the world? Do you think that wave functions are merely a way for us to record what we don't know? Are they merely mathematical? Are they an expression of laws? But you're supposed to start with the wave function and then go from there. I would challenge that paradigm and not just challenge it in the sense that that people are doing something wrong. The truth is, as students move through an education in physics, they'll begin to see that this paradigm is really too simplistic. when students finally encounter the full axiomatic definition of quantum theory, they'll see that there's really a lot of other ingredients at play. And the simple picture that the story is about wave functions begins to dissolve to some degree, even though the wave function does continue to play a very important role. A number of years ago, I got very interested in trying to understand quantum mechanics, understand where the theory has places that it's either ambiguous or potentially inconsistent. I got very interested in old questions like the famous measurement problem. What counts as a measurement in quantum mechanics? That's important because the axioms depend on this notion of a measurement, which the axioms don't define, in order to get predictions out of the theory. And because there's no rigorous definition of what a measurement is, there's this very important feature of the axioms that we kind of activate only when we know when we see it, that sort of a thing. There's some situations, and maybe we'll talk about some of them, some thought experiments where you confront some of the ambiguities in the theory. And I got very interested in a mathematical reformulation of quantum mechanics, the so-called algebraic reformulation of quantum mechanics. And there's a lot of sort of esoteric mathematical terminology and definitions that's involved here. This is the C-star algebraic formulation of quantum mechanics, which provides a very different way to think about the foundations of the theory, what the theory is and how it works. And it relegates some of the ingredients that I think students in particular first see in quantum mechanics to a somewhat more secondary role. In particular, the place where wave functions are supposed to live. And here I'm eliding some terminological distinction between wave functions and state vectors. Some people make a terminological distinction between them. Some people use them more or less synonymously. But whether you call them wave functions or state vectors, they live in these abstract spaces called Hilbert spaces. And in these algebraic formulations of quantum theory, you don't start with Hilbert spaces. You start in a very different place with a different kind of mathematical structure. And the Hilbert space picture is sort of a derived emergent feature of these algebraic formulations. And for me, this was very helpful in beginning to think outside of this so-called wave function paradigm, that there are in fact other ways to think about quantum theory, ways that don't begin with wave functions or the places, the abstract places where they live, Hilbert spaces. And this sort of cracked open the door a little bit. It opened my mind to rethinking some of these ideas. And once you crack open the door a little bit, it becomes easier to imagine totally different ways of thinking about quantum mechanics. The algebraic formulations are very useful and very powerful. You can do some very interesting things with them, and they turn out to be very convenient for certain kinds of quantum systems. But for me, this was more, like I said, it opened up my mind to new ways of thinking about quantum mechanics. And so the project I'm working on right now is really not about C-star algebras or the algebraic formulation, but it is very much a formulation in which, once you realize that Hilbert spaces are things that can be derived, it's hard to forget that.
So has anybody built up to a Hilbert space before? I mean, does it feel like it just kind of emerged and took you by surprise too when you were playing around with the math?
Actually, I'm not by any means the first to realize this. The traditional way that quantum mechanics is formulated is there's this abstract space, a vector space called the Hilbert space. That's where quantum states, wave functions are supposed to live. Quantum states are supposed to evolve in a particular way according to a particular law. In the simplest case, that's the Schrödinger equation. And then there are all of these measurement axioms which specify, what are the mathematical objects that represent the things we can observe, and then what are the rules for calculating the probabilities with which we observe their values, and then what do we do to the quantum state once we've done a measurement. Those are basically the axioms of quantum mechanics. But, well before me, people realized that you could take some of these mathematical ingredients, abstract them away, imagine lifting them, so to speak, conceptually, metaphorically, lifting them out of the Hilbert space picture, and regarding them as mathematical ingredients in themselves. And what you get is an algebraic structure called a C-star algebra. I keep saying that it's not a C-star like on the beach, it's capital letter C star. The C stands for closed. It's closed in a certain mathematical sense that there are no holes in the algebra. And if you have a sequence of elements that approaches something, then the thing they approach is also still the algebra. It makes the algebra like a complete closed thing. And the star just refers to a certain operation you could do on the elements. For those listeners who are familiar with complex conjugation, the star is kind of a generalization of complex conjugation. Anyway, these algebras are called C-star algebras. They have a number of other mathematical properties that you need them to have. And if you formulate a quantum system directly in terms of an algebra like this, without ever mentioning a Hilbert space, then it turns out there's a theorem. It's called the Gelfand-Neymark-Siegel theorem, or the GNS construction. This construction generates a Hilbert space out of this algebra of quantities. Now, this algebra of quantities has a very concrete meaning. Each element of the algebra refers to a particular thing you could go out and measure on your system. And so those have a more concrete meaning. And the Hilbert space that sprouts out of them through this really beautiful theorem. The GNS theorem is a beautiful theorem. For your listeners who are interested in mathematics, in particular, may have some interest in functional analysis or operator theory. Many of them probably will have heard of the GNS construction. For those listeners who haven't heard of it, it's really a beautiful theorem, and worth getting to know if you're interested in quantum mechanics or in linear algebra. But the idea that the very abstract, exotic ingredients of Hilbert spaces emerge from this algebra, this set of algebraic ingredients that have a more concrete meaning, that you start with the algebraic ingredients where the elements refer to things we can go out and measure, and then this exotic Hilbert space structure sprouts out of it through this theorem. That's been known for a very long time. The GNS construction goes back over half a century. And periodically, people who think about quantum mechanics in these terms are often quite amazed that you can do this, and that so many of the things that we often take for granted, again, like Hilbert spaces and all that structure, can be seen to be emergent from a deeper level of structure.
So, it seemed like one of the big things that Einstein was so good at early on in history was just imagining something and then trying to put a logical vision together of how the universe might work and then building from that. And then it also seems like at certain times these kind of visuals have also hurt different fields because they've been forced into the mathematics. Like, what are your thoughts on how visual we can kind of imagine some of these things, or do you have certain metaphors or images that are driving your work right now?
So that's very interesting. So visuals can be helpful, they can be harmful, just for all the reasons that you indicated. Sometimes they help guide our intuition, and sometimes they lead to tunnel vision. Tunnel vision is a very dangerous thing when you're trying to do foundational work, especially even if you have a lot of experimental data to help guide you, tunnel vision can make it very difficult to be open-minded enough to see the data, and maybe come to conclusions about it that are very different from your starting place. But, if you're not guided by a lot of data, if you have a lot of theoretical constraints, you've got a lot of theories that we have and that fit the data we have, but there are places where our theories don't quite work. Now, of course, one attitude is just to say, well, until we have data, we can't do anything. And that may be true. In some cases, that's true. In other cases, we can be guided by an attempt to patch up inconsistencies in our theories. And Einstein was a good example of this. Einstein was certainly motivated by experimental data at many points, but in some situations, he had theories that he knew and trusted, but they didn't quite work. And in trying to get them to fit together in a logical way, he resorted not to experimental data in all cases, but sometimes thought experiments, logical analysis, rigorous scrutiny. Many of the tools that I would argue are the tools of someone trying to do science with a background of a philosopher, trying to approach problems in a very rigorous, scrutinizing kind of a way. But when trying to do that, especially if you're not guided by a lot of data, you have to be very careful about being misled by imagery. Einstein certainly used a lot of imagery. His thought experiments were very visual, so that can be good. But again, you have to be on your guard. So there's some places where I think being able to visualize things is helpful.
And do you have a visual mind? Because it seems like you have this philosophy background and this mathematics background. But are you, like, when you're thinking to yourself in your own head, are you speaking in words, more in numbers, or more in full visual imagery?
I guess kind of a combination of all of them. Some of it is mathematical, some of it is verbal, I suppose, where I talk myself through things, and some of it is visual. I do visualize what's sort of going on here. And that's kind of part of the goal. So let me first give an example of where I think visuals can be misleading.
Tell me about the vision.
So here's a place where visuals can be misleading. If you open up the beginning of Feynman's lectures on physics, volume 3, and some of your listeners may be familiar with Feynman's lectures, famous, fantastic lectures. You open up volume 3, It begins with a discussion about quantum mechanics. And it starts with a discussion of the double-slit experiment. Now, the double-slit experiment is something that people who have some familiarity with quantum mechanics, even at the popular level, probably have heard of. The idea is that we send small particles, microscopic particles, electrons or photons, or even atoms. We send them into an apparatus in which there's a wall with two small holes in it, two small holes close together. A lot of the time, the atoms will simply miss the holes and bounce off, but occasionally they'll go through the holes. And then far away, behind this wall, is a detection screen that simply tracks where the atoms land when they arrive at this detection screen. And in this experiment, we send one particle in at a time. And so every run of the experiment, you get one dot on the detection screen. And you do this experiment many, many, many times. Let's say 10,000 times. And you end up with lots and lots and lots of dots. And you look at the pattern of dots, and you're a little bit confused. Because if you did this experiment with tiny stones, you would imagine getting a large accumulation of dots sort of in the middle of the detection screen, and fewer dots as you go away from the middle of the screen. Remember, the two holes are very close together, so any rocks going through one hole or going through the other, are mostly going to end up near the middle of the screen. That's what you expect, and that's what you see when you do the experiment with classical particles like stones. If you do this experiment, in fact, with very microscopic particles like electrons or photons, what you get is a very puzzling-looking distribution. You see places on the screen where there's an accumulation of dots and places where there are very few or no dots. And they form bands with a strong accumulation sort of in the middle, and then a so-called node or region where there are very few dots, and then beyond that, another region of a lot of dots, and then a region of very few. You get this sort of almost periodic-looking pattern of peaks and valleys in the dots. Now, it's very important to note, you're not seeing a wave here, literally. You're seeing dots, but the dots form a pattern that looks kind of like a wave-like pattern.
And something that feels like evidence of a wave.
That's exactly right, yeah. And if you did this experiment with, say, water waves, if you sent water waves through two small slits, or you did this experiment with classical light, you send an actual classical light through this sort of experiment, you'll see a very similar looking pattern. And so it's very easy to look at this pattern and say, gosh, this must mean that an electron really is, in some sense, also a wave, or it goes with a wave, or it's replaced with a wave, or it has wave-particle duality. It's a little unclear exactly what we're supposed to think about this, but there's some wave-likeness to the electron, or the photon, or whatever the individual quantum particle is. And that's why we get this pattern. Of course, we don't get the whole pattern in any one run of the experiment. Every run, we get one dot. But you do this experiment many, many times, and you're looking for some explanation of why we get this kind of a pattern. Now, the most flat-footed way to think about this experiment is the particle is, in some sense, a wave propagating in physical three-dimensional space. It approaches the holes. It goes through a process called diffraction, where it kind of leaks out of both holes, and you get two spherical-looking growing waves coming out of the holes. And these spherical waves have some places where they constructively interfere, which means they get stronger, and other places where they destructively interfere, they get weaker. Where, one wave is a peak and the other is also a peak, you get an even taller, brighter wave, and when one is a peak and one is a trough, you get a weaker wave, you get destructive interference. And if you just look at where the places of constructive and destructive interference are on the detection screen, they seem to line up pretty neatly with where the dots are. So one way of thinking about this is that the electron is a wave for most of the experiment, but then when it finally reaches the screen forces the electron to pick a place to be. And at that moment, the electron goes from being a wave to being a particle, a point-like particle, and registers one spot on the screen somewhere. And where it's probabilistically most likely to be found is where the wave is the most intense. And this connects with this idea that there's some relationship between the intensity of these waves going through the holes and the probability of where the electron will be found when it's measured. So one way to view this experiment is the electron is a wave, it goes through, it diffracts, you get this interference pattern, and then a measurement is done on the location of the particle, and the particle is probabilistically likely to be found at this precise at one precise location with a probability that is related to how intense the wave is. As you do this experiment many times, and then you build up this pattern of landing sites. Well, this raises a lot of questions like, the electron was a wave and then it becomes a particle. This is supposed to be an indication of wave-particle duality, but what's going on there? Why does it go from being one to the other? But nonetheless, this is still supposed to be a visually helpful exercise. And it's supposed to convince you that electrons in some sense are wave-like and that the wave function is a physical thing somehow. Mm-hmm. Now, there are immediately some questions you might raise about this. One is, you can't actually see the wave function directly.
Yeah, so what is it?
But this is often, oftentimes people will just show you the pattern of landing sites, not the individual dots, but like the distribution, and that makes it look like in an experiment you're seeing the waves. Now, if you do this experiment with water waves or with classical light, you will see the whole pattern, but when you do the experiment with individual particles, you see one dot at a time. You don't see the wave. That's curious. And it turns out that there's nothing you can do to see the wave directly. Now, I'll make it very clear, because people may say, well, I read this experiment once where they were showing the wave function. There are lots of indirect experiments you can do that show patterns that do look a little bit like a wave function. But like this experiment here shows like a pattern that looks almost like a wave if you look at all the landing sites. But there's actually some pretty fundamental reasons why you cannot see the wave function. So here are some fundamental reasons why you cannot see the wave function. For one thing, the wave function is not real valued. The wave function assigns numbers to possibilities, and the numbers it assigns are not ordinary real numbers like 5 or -2 or square root of pi. They're so-called complex numbers. They're numbers, sort of formal abstract numbers of the form ordinary, good old real number plus the square root of -1 times an ordinary real number. Now, the square root of -1 is called I. It's the imaginary unit. It's the fundamental imaginary number. And imaginary numbers are not scary things. They're not even that exotic. And there are a lot of videos on YouTube trying to motivate how to think about complex numbers in a way that makes them seem less strange or unusual or unphysical. And that's fine. I mean, they're not scary or exotic. But they're not the things we directly measure out in the world or the things we directly see. They have their nature is a little bit more abstract than ordinary numbers. That's already something that's a little bit odd. But the other problem with wave functions is that they don't actually live in physical space at all. And this is a point that, again, people who go and take a lot of quantum mechanics courses will eventually realize. But when you take your first course in quantum mechanics, you spend probably a lot of the course looking at a single particle in one dimension of space or 3 dimensions of space. And it happens that for a single particle in 1 dimension of space or 3 dimensions of space, the wave function is a function of 1-dimensional space or 3-dimensional space. And so it's kind of like a field, like an electric field, in the sense that it's an assignment of things to points in physical space. And the things it's assigning is, if I measure where the particle is, then the wave function, the value of the wave function at that particular point in physical space, is a complex number that when I do a certain operation on it, it's called a mod square operation, you get the probability density with which a measurement will find the particle there. That's what the wave function is telling you. And it assigns one of these complex numbers every point in space, and that number at every point in space, each point in space, is telling you the probability that a measurement will find the particle there. So you get this feeling like a wave function lives in physical space. It goes through the double-slit apparatus, it diffracts, it moves around in physical space. But the moment you consider 2 particles, now the question you're asking about measuring like location for 2 particles is, where are the 2 particles? That's now 6 numbers, not 3 numbers. And it turns out that the wave function for a system of 2 particles does not live in 3-dimensional space. It lives in a 6-dimensional space. You need a dimension for every one of the coordinates. And if you wanted to consider a system of n particles, where n is some number 1, 2, 3, 4, some number bigger than 1, let's say, then the wave function is a function that lives in 3 n-dimensional configuration space. Yeah.
That's so, yeah, okay.
Yeah.
I mean, I'm just trying
and
to
we
wrap my head
don't
around it,
apparently live there. So we can't visit
Yeah.
this possibility space or configuration space and see wave functions there. And the fact that the wave function looked like it lived in 3D space when you had one particle was actually just an artifact that follows from the fact that for one particle, configuration or possibility space happens to be the same number of dimensions as physical space, and so you can confuse them. So we can't see wave functions because they don't really live in 3D space at all. If you now rerun the double-slit experiment, but now do 2 particles or 3 particles or 4 particles, suddenly the visualization, the wave visualization, is not very helpful anymore.
No.
Because with 3 particles, let's say, the wave is propagating in a 3 times 3, 9-dimensional space. I don't even know where the holes are supposed to be. Right, you can't visualize it. So if you take the visualization in the 1 particle case too seriously, you get a kind of tunnel vision. You begin to think too seriously about wave functions. You have trouble giving them up. But if you right away were to consider waves and particle more than 1 particle at a time, you would realize pretty quickly that this is actually not a helpful visualization, and maybe we should rethink the seriousness with which we take waves. There's a letter, a very famous letter from Albert Einstein to his colleague Max Born, December 4th, 1926. In which Einstein is saying to Born, quantum mechanics is certainly very imposing, but I for one don't think I still don't think it's the real. I think the word he uses is the real Jacob, but he means the real thing, the real McCoy. But I happen to like he says the real. I guess he says the real Jacob.
Yeah. Might as well put.
Yeah, exactly. I'm not sure it brings us any closer to the mystery of the Great One. I don't believe that God. I don't believe that he throws dice. This famous, I don't believe God plays dice. But the next sentence in that letter is Einstein complaining to Max Born, as he had complained to several other contemporaries at the time, to Lorentz and other people. He said the next sentence is that he can't believe that the seat of physical reality is supposed to be waves in a 3n-dimensional space with a potential energy, like with rubber bands. He trails off and he's not even sure what to say about this. And unfortunately, when this letter was translated into English in the canonical translations, the N was lost in the English translation. And so it just looks like Einstein is complaining about waves in 3D space, which would be a very funny thing for Einstein to complain about. He was really worried about waves in 3n-dimensional space. Anyway, so I'm not the first person. Certainly I'm not the first. Lots of people have when they've looked at this, find the idea that physical wave functions being real objects, metaphysically or physically real objects, let alone mathematically real. I mean, they're complex, valued mathematically, but physically, metaphysically real. That does not make a lot of sense, and maybe we shouldn't take that too seriously.
So does that still bother you, or do you kind of identify with Einstein, or do you feel like he wasn't able to get comfortable with the kind of thing you can get comfortable with now in modern day physics?
It's very flattering for you to suggest any commonality between me and Einstein here, but Einstein wasn't the only one who had problems with this view. Schrödinger, who had introduced his wave function in 1926, and in a beautiful paper that's in English. I mean, he wrote also in papers not in English, but he also, one of his fundamental papers on this topic was in English. He called it, the paper is 1926. It's an undulatory theory of atoms and molecules. I recommend that people look at it. It's a beautiful paper. It is technical in some places, but there's a lot of very beautiful exposition in the paper. Schrödinger knows right away that his waves live in 3n-dimensional configuration space. He's very clear about this. He calls it Q space because Q is usually the variable used to represent configurations. And he seems to bite the bullet and say maybe this is the seat of reality, and we need to find some explanation for how waves in a high-dimensional possibility space somehow project facts down to ordinary 3-dimensional space. And he has several proposals for how this is supposed to work. And this view, this idea of bringing waves into physics and differential equations was very amenable to the physicists at the time. They really liked this compared with some of the other approaches to quantum mechanics that were developing at the time. But Einstein didn't like this idea, and Heisenberg didn't like this idea, and it was one of the few things that they apparently agreed on. But by 1928 or so, Schrödinger gave a lecture, his 4th lecture on wave mechanics, and he has a section called On the Interpretation of the Psi Function. Psi is the Greek letter. It looks like a trident symbol. It's his symbol for the wave function, in which he says, I used to think that the wave function was a mechanical thing. It really existed in this high-dimensional space. And maybe it was representing an arena where all the possible mechanisms, all the possible things the system could be doing were all playing out in some sense, in kind of an embryonic version of the many worlds interpretation. But this is, not long after Max Born, who Einstein had written that letter to in 26, Max Born had introduced the idea that the wave function was really telling you probabilistic information. It wasn't a physical object. It was really encoding information about the probabilities of measurements. And so Schrödinger by 1928 says in this section where he's describing, his view on his wave function, that he no longer holds the view it's a physical object. So he apparently recanted that view, but I think some people continue to recant that view. The Copenhagen interpretation that's usually associated with Heisenberg and with Bohr, Niels Bohr, and with Max Born also relegates the wave function to a non-physical status as just a mathematical tool. But I think the idea that wave functions are physical objects in a high-dimensional space, either configuration space or somewhat more abstractly nowadays in a Hilbert space, which is an even more abstract space where, in some sense, state vectors, which are sort of the formalizations of wave functions where they live, the idea that they're physical objects, I think, took hold. And I think a lot of people, certainly coming into physics, newcomers, and even people who work in the area, I think they ascribe a physical meaning to wave functions, at least some people. I don't want to make blanket statements here, but I've certainly encountered people and met and spoken to them who think that wave functions are physical objects. And I think that view goes back, like I said, to Schrödinger's early work that even he didn't continue to hold.
Well, it just seems so interesting to think about that this dimensionality just blows up, right? Like it's just 2 particles, 3 particles, 4 particles, and then a trillion or so that would make up anything at the level of sufficient complexity that would be called a human that could think or move around. It just seems like so big that, either is reality projected down, meaning sort of like a structure is what we experience, or is it more like we're the remnants that get left in just the 3 dimensions after you do all this multiplication? What is
I don't claim to know
floating around me?
Yeah, I don't claim to know because even Schrödinger never quite figured out what the how to understand reality as somehow being emergent or derivable from this abstract structure. I should say that it does get worse when you regard. So for one thing, our modern most comprehensive fundamental physical theory of the non-gravitational interactions, all the other kinds of elementary forces, is described by the Standard Model of particle physics, which is a model written in the formalism of what's called quantum field theory. The systems that the Standard Model consists of are quantum fields. And quantum fields are not fundamentally as formalized. They're not fundamentally defined as particle systems. There's one view that particles are approximate emergent fluctuations, energetic fluctuations in these fields. The photon is a kind of fluctuation, a quantized fluctuation of the electromagnetic field. The Higgs boson is a quantized fluctuation in the Higgs field. And so if particles are not the fundamental things, there isn't a well-defined number of particles in the universe. It kind of depends on what time you're asking and what system you're looking at. And so if there isn't even a fundamental number of particles, there isn't really a wave function that really that lives in a space of any dimension at all. At best, maybe there's something like, maybe a quantum field as a whole has a wave function, but that sort of a wave function would formally be like in an infinite dimensional space because wave functions have infinitely many moving parts. And this is even thinking in terms of wave functions. If you, again, go from configuration space to something like a Hilbert space, which is an abstraction of, where we think quantum states, when the theory is formulated axiomatically, we actually talk in terms of elements of this even more abstract space called the Hilbert space. Then the Hilbert spaces have even higher dimensions. Even for a single particle, the Hilbert space is formally infinite dimensional, let alone for multiple particles or quantum fields. So, you talk about complexity, you talk about we're talking about objects that live in incredibly high dimensional abstract spaces, in some ways formally infinite dimensional. And then you ask how we're supposed to think of the physical world emerging from them. It's a very difficult authority question.
Yeah, well, just coming from more of the AI kind of background and just thinking about how these higher dimensional representations of intelligence and patterns kind of play out, there's just something sort of tantalizing about the 2 fields that just kind of make me curious. But I'd love to hear the story of Wigner's friend. It seemed like something that really resonated with me when you've talked about it before and kind of helps see what could be wrong with some of the ways we think about quantum mechanics.
Great, yeah. So one way to think about Wigner's friend is we're going to set up a flowchart, one of those decision tree flowcharts with lots of yes or no questions that are going to take us into various directions. And I won't need to draw a diagram. It's a simple enough flowchart that I could just say it in words. So the Wigner's friend experiment is intended to exploit a certain ambiguity in the axioms of quantum theory. So if you think that the only problem with quantum theory is aesthetic or philosophical, we don't need to worry about this. Wigner's friend is supposed to give you a thought experiment where, at least in principle, even if this is practically going to be very difficult to do, but in principle, we can set up a situation in which the axioms are ambiguous about what you're supposed to do. And if there's an ambiguity in the axioms, this is a real inconsistency that needs to be addressed. Wigner's friend's thought experiment apparently goes back to Hugh Everett's long-form unpublished dissertation, his 137-page dissertation. Curiously, 137 pages, which is also the reciprocal fine structure constant at low energies. Just an interesting numerological coincidence. But in this long-form unpublished thesis, he opens it up with this thought experiment. This is around 1956, 1957. He was at Princeton working for John Wheeler, but he was also there at the same time as Eugene Wigner. And a few years later, Eugene Wigner writes a paper called Remarks on the Mind-Body Question, where he this is 1961, where he formulates a very, very similar thought experiment. So people now call it the Wigner's friend thought experiment, but I guess you might say that it's really better attributed to Hugh Everett. It doesn't matter. They're both at Princeton. They're probably talking with each other. But in this thought experiment, we imagine two observers. And the moment you've got two observers, you're going to start running into questions about, well, if there's two of them, and what if only one of them does a measurement and not the other? What are we supposed to do? The axioms now are a little bit confusing. I listed the axioms before: Hilbert spaces and quantum states, smooth evolution. Those are the first two axioms. And then the measurement axioms are, when a system is being measured, you've got these abstract mathematical objects that represent the things that could be observed. Then you've got a rule for getting the probabilities out. It's called the Born rule. And then finally, after the measurement is done, you're supposed to collapse the quantum state to reflect the outcome and give you a robust result that's then repeatable. So those are the measurement axioms. And the problem is they depend on this notion of a measurement. What counts as a measurement? What kind of interaction counts as a measurement? What kind does not? And if you're ambiguous about this, then you can set up situations in which you really can't decide which is true. So you have two observers now. One does a measurement, the other does not. And now we have to ask what we're supposed to do. And to make this thought experiment as precise and idealized as possible for the purposes of this argument, we put one of the observers inside a perfectly sealed box, and one of them is outside the box. The one outside the box is Wigner. Wigner with a W, so capital W, Wigner. And the person inside the box is Wigner's friend, F for friend. And the box needs to be sealed at least well enough that during the course of the experiment, there's any information exchange between the interior of the box and the exterior is negligibly small. In practice, this is extremely hard to do because even if the box is a little warm, there could be thermally radiated photons leaking out of the box. You have to shield the box from that, at least for the duration of the experiment. So this is practically very, very, very difficult to do with observers who are human size. And I don't know the latest on exactly how long it might take for us to realize this, but this is a thought experiment. It's an in-principle question. Wigner's friend on the inside of this box that is sealed for the duration of the experiment does a quantum measurement on a superposed quantum system, a quantum system that is in a superposition of one, a value of one observable and another value of that observable. And Wigner on the outside does not do a measurement. Wigner on the outside is sealed off from what's going on inside the box, does not know the outcome, knows no information about it, is not exchanging any information, and does not do a measurement.
The one inside the box could be like cat is dead or alive, right?
That's right. In fact, the one inside the box, Wigner's friend could just be a cat who's smart enough to do an experiment. I mean, but the point is that Wigner's friend in the experiment has to be something that can do a measurement, at least that we would all agree is capable of doing measurements. Even though we don't have a definition of measurement, so this is the problem. You have to just, something that we would all agree counts as a measurement. And now we've got a problem. What are we supposed to do with the quantum state? I mean, we have two observers. What are we supposed to do here? And you have basically a flow chart you can now set up. Okay, so here's the flow chart. Question 1, yes or no. Do we collapse the quantum state of the overall system? Should Wigner on the outside, who is studying this whole system, this sealed box, should Wigner on the outside say, well, I know my friend in the box just did a measurement, because we arranged this beforehand, we agreed this person would do a measurement, so should I, in some sense, collapse what's going on in this box? Now, the collapse doesn't mean knowing what the answer was, but it does mean replacing the original quantum state with a so-called Luder's projected quantum state, which is supposed to be the quantum state that results from a collapse. When this collapse happens, you lose what are called interference effects. They disappear. There's like a very clear meaning for this. And we now have two classically distinct possibilities, one of which is the true possibility of how the experiment went. Yes or no, do we do this? Yes or no? If the answer is yes, then we run right into the measurement problem. Because Wigner's friend in the box, did a measurement, but what if we'd replace Wigner's friend with a somewhat simpler system, a simpler mechanism, a small robot, or an amoeba, or a virus, or a nano robot, or a complicated arrangement of buckyballs, or a small number of electrons. At some point, we go from measurement to not measurement, and now we have this so-called Sorites paradox, this heap problem. Like, when is it a measurement, when it's not a measurement? But we actually need to know, because we need to know whether or not to activate this axiom. There doesn't appear to be like a middle way between activate the axiom and not activate the collapse or measurement axioms. So this is just the measurement problem. If you say yes, the state was collapsed, then you now have the measurement problem. It is on you to determine what kinds of systems actually can do collapsing measurements and what kind cannot. And this measurement problem has been around for a very long time, century or more, and I guess probably around a century at this point. If you track it, it's the beginning of modern quantum mechanics with Heisenberg's paper in 1925. It's been around a very long time, and we don't have an answer, and arguably we're not going to find an answer. But at a deeper level, there appear to be other phenomena happening in the world that are not measurements anyway. Gases mixing in the early universe, birds foraging, the galaxies colliding in the far future. These don't ostensibly seem to be measurements, but they do appear to be happening. And yes, we only know they're happening because we do observations, but are we going to go full anti-realist and say that our observations do not allow us to infer anything about what's going on in the world? If we're really going to go and say that nothing is happening in the world except just our observations, that's a very strong move to make, and it immediately runs into the problem of being self-undermining, because if nothing exists, why do we exist? I mean, what's special about us? So that's like a really tricky argument to be made. But if all these other things are happening, then either you have to show that they are in fact all measurements, which, good luck, show they're all measurements even though there's no measuring devices involved for most of them, or admit that quantum theory is not capable of accounting for the much larger category of phenomena that are not measurements. I call this the category problem. The textbook axioms only describe the small category of measurements. All the averages we compute in quantum mechanics are measurement averages. And we somehow, would like to be able to account for the much larger category of phenomena happening. So if you take the first option, yes, you say, yes, the thing collapses, you have to deal with all of these problems, and they're all serious problems. Okay, so now suppose we say no. Wigner does not collapse. The wave function of the overall box is not collapsed. Okay, now we have another question. Despite the overall wave function not collapsing, was there in fact a result of the measurement? Right? Despite the fact that there wasn't a collapse of the overall wave function of the whole system, of the box and everything in it, is it still nonetheless the case that Wigner's friend achieved a unique single measurement result? If that's your view, then you're saying that Wigner's wave function is incomplete. It hasn't changed. It has not changed to reflect like the fact that there is in fact a unique specific result of the measurement. So it's incomplete. There is more information in the story than is reflected, that is contained, that is encoded in the overall wave function. And that extra information is by definition called a hidden variable. So you are now subscribing to a so-called hidden variables approach to quantum mechanics. And there are several hidden variables approaches. Bohmian mechanics, the pilot wave theory of de Broglie from the 20s and Bohm in the 50s, is probably the most well-known hidden variables theory. The modal interpretations are less well-known. They go back to the 60s. Henry Cripps had the first modal interpretation in like 1968, but then there were others, Bos von Frossen and Dennis Deeks and Peter Vermas and lots of other people who worked on the modal interpretations. They've fallen somewhat out of favor over time. I worked on them about 10 years ago. So they're modal interpretations. There are other kinds of sort of perspectival hidden variables interpretations. I don't know whether you could view relational quantum mechanics as a form of this view. I think that's disputable, but nonetheless, that's one particular avenue that one could take. So that's if you say that there is in fact a fact of the matter, there was a definite unique result of the measurement that is not reflected in the overall wave function of the whole system, then you're agreeing that you are going to go for a hidden variable, so-called hidden variables approach. Hidden is a little bit of a misnomer because, I guess in some sense it's hidden from Wigner on the outside, but it's not hidden from Wigner's friend on the inside. It's just a sort of a term of art.
Yeah, right.
Some people call them additional variables. I like to call them physical variables because they're additional if you think there's also a wave function as a physical object. But if, like me, you don't think wave functions are physical, then they're not additional to anything. So you could call them physical or ontological, meaning that they exist, or ontic is another adjective meaning they exist variables.
Okay, so what progress have you made? I mean, when we talk about stochastic processes, maybe helping these descriptions, can you walk me through what that means or what your thoughts on it currently are?
Yeah, great. So stochastic approaches. So I should make very clear here, I'm not saying that there is a physical wave function that's stochastic collapsing. Some people, when they talk about stochastic and quantum, they think that's what we're talking about. These are quite different. They're much more like Bohmian mechanics in the sense that you've got physical ingredients. If you're studying a system of particles, then it's particles. If you're studying a system of fields, it's field intensities. You have to pick whatever configuration it is that you're talking about. But once you've picked the configuration, the kind of configurations that you want to model, you have to come up with laws that describe how those configurations are supposed to change with time. And those laws should be just right so that they carry the configurations to the right places so that you get agreement with the predictions of textbook quantum theory. You get the correct probabilistic predictions. Bohmian mechanics does this by saying that first we find the wave function of the system by solving a particular differential equation, the Schrödinger equation, or some appropriate generalization, and then we take the result of that, the wave function, and put it into a second equation called the guiding equation. And the guiding equation is supposed to be the thing that tells the particles how to move. And actually in a deterministic way. The probabilities in the Bohmian approach come from uncertainty over where the system begins. We start with a so-called initial equilibrium probability hypothesis about like how do we express our uncertainty probabilistically about the initial configuration of the system, and then the wave function pilots the ingredients, the particles, the arrangements of particles to where they're supposed to go, and then where they arrive. The locations of where they arrive inherits probabilities from that initial uncertainty, and the probabilities that are inherited exactly coincide with the Born rule probabilities that come out of the axioms of quantum mechanics. But it's a little complicated. You need this guiding equation in the middle. The guiding equation seems in most formulations to single out a preferred reference frame. And in special relativity, people may know that special relativity treats all constant rectilinear motion as being on the same footing. At least locally in our universe, if you ignore the overall like cosmology. If you just look at local regions of space, you shouldn't be able to tell the difference between someone at rest and someone moving relative to the first person at a constant rate. And the fact that the guiding equation seems to pick out a particular preferred notion of rest is not obviously empirically impossible, but is certainly in strong tension with special relativity. But the bigger problem for me is not that aesthetic issue. The bigger problem is that we don't have a really good generalization of Bohmian mechanics beyond systems of fixed numbers of finitely many non-relativistic particles. Those are the kinds of systems that Bohmian mechanics seems very, very good at dealing with. And trying to generalize the theory to quantum fields or more general kinds of systems has proved very difficult to do in a self-consistent way that's able to accommodate the standard model and like realistic-looking quantum field theories. David Wallace, the philosopher of science at University of Pittsburgh, has given a bunch of talks in a paper basically saying that the sky is blue, and that's because of Rayleigh scattering, which is the story of how light interacts with the charged particles in our atmosphere in the air and scatters off in a way that is frequency dependent and favors certain frequencies, which is why we see much more scattering in the bluish part of the spectrum than in the other parts during most of the day, and that's why the sky looks blue. And his argument is that approaches like Bohmian mechanics and even some of the dynamical collapse approaches don't seem to have the resources to be able to account for something so important and so prevalent and so simple, and this means that they have not achieved empirical adequacy. They have not reached to the level of being able to account for the things that we see. That to me is a much more serious problem. We have aesthetic problems you can have with a physical theory interpretation, but empirical adequacy, in my view, is not aesthetic. It's not just a preference. A theory has to be empirically adequate, which means it has to account for the things we observe experimentally. If it cannot do this, that's not just a matter of preference. That means the science is not so good. So my approach is a bit like Bohmian mechanics. If you wanted to model a system of particles, it would be very similar. You'd start with particle arrangements. Those would be your configurations, the so-called ontology of your theory. The things that you're saying exist are where particles are, their arrangements in say, physical space. But now the laws are going to be different. Rather than the laws being you first solve the Schrödinger equation, get the wave function, plug the wave function into a guiding equation. The guiding equation tells the particles what to do. We just throw all that out. Now, we just let the particles evolve stochastically. We give just direct laws. The particles are just moving around on stochastic trajectories. They're just, probabilistically going to their next places in such a way that we get the same predictions as you would get from standard quantum mechanics for the probabilities that measurements will come out in the correct way. And so the question is, can we come up with stochastic laws that empirically agree with the predictions of quantum theory? That's what this comes down to. And in the 1920s, the early 1920s, people didn't seem to be able to come up with laws that would do the job. That said, this was very early on in the development of probability theory. We're talking the early 1920s, leading into 1925 and 1926. Quantum theory, as we know it, was formalized by Paul Dirac in 1930 in his book, and then John von Neumann in 1932 in his book, respectively, Principles of Quantum Mechanics in 1930 by Dirac and Mathematical Foundations of Quantum Mechanics by John von Neumann in 1932. And Kolmogorov didn't formalize his axiomatic theory of probability until a year later in 1933. And stochastic processes, that whole theory took decades to develop. So quantum theory as we know it was already very solidified, arguably calcified by that point. That said, there were people over the years who attempted to see if you could get rid of all that formalism and all that stuff and just have a direct theory of stochastic laws that were just right to give you the same predictions as quantum theory would, just directly acting on the constituents. And actually, in Hugh Everett's long-form dissertation, he talks about an effort by Fritz Bopp, in the 1940s to do that. Everett actually says it's a promising direction. He says some very interesting things about it, but doesn't discuss it much more. Spends his thesis talking about his many worlds interpretation, as it would later be called. And then there were others, Imre Fenyes in the 1950s, roughly, and most famously Edward Nelson in the 1960s. These approaches tended to be very, very complicated. The stochastic laws they wrote down were very, very intricate, with lots of parts. Sometimes they would require you to find the wave function like you would in the Bohmian approach first, and then plug that in to get the laws. And the laws had lots of, they looked very, the word is gerrymander. They were like very carefully designed to after the fact agree with the predictions of quantum theory. And so it was hard to motivate them except to say that you already knew what you wanted from quantum theory and you were just going to go and carefully design laws that would, as best you could, approximate the results that were supposed to come out in the traditional textbook approach to quantum theory. And like with Bohmian mechanics, it turned out to be very hard to generalize these theories to systems beyond systems of fixed numbers of finitely many non-relativistic particles. So these efforts were not widely studied. There have always been a few people who've worked on these approaches, these so-called stochastic formulations of quantum theory. And even to this day, I'll encounter people who will say, I'm still working on this, I think it's promising, and I agree. I think people should work on all of these things. What happened to me was I wasn't trying to study one of these approaches. I was engaged in a much less high-minded exercise, but one that was very meaningful to me, at least. I was trying to teach a class of students who were very new to physics, who didn't have a lot of background. A lot of them did not yet know linear algebra, which is the mathematics of vector spaces that often is used in quantum mechanics. And so they didn't have a lot of background, but they were very curious, and I wanted to tell them something about quantum theory with the limited mathematical tools that we had available to us. They knew something about probability, and so what I tried to do was sit down with the classical theory of stochastic processes like you might find in a textbook. For those people who've ever built a Markov chain Monte Carlo simulation, people working in computer science, in AI, maybe they've used probabilistic systems like this, may have some familiarity with this sort of a thing. And I just was curious, right? Because these frameworks, they've got matrices in them, they've got vectors in them, they've got probabilities in them, they have random variables, which are like observables in them. They have a lot of features that, in very vague ways, seem to resemble the mathematical structures that one has in quantum theory, which also has vectors and Hilbert spaces, though, but has observables, which play kind of the role of random variables. It's got probabilities and so forth. It's got time evolution. It's got things that carry matrices that carry out time evolution. So I just sat down and I'm like, maybe I can tell them a little bit about the theory of Markov chains and stochastic processes, which is a little more familiar. It doesn't have complex numbers in it. The vectors are just simple vectors of probabilities. It's much simpler. Maybe I can somehow take that formalism and the formalism of quantum mechanics and Hilbert spaces and just make them look more similar. I can just sort of like rewrite one, rewrite the other, rewrite one, rewrite the other, rewrite them in a way that I can almost get them to look almost the same. And then I can just say, okay, now that they're almost the same, I can pinpoint exactly the assumption we have to change or drop or modify or add to get from stochastic processes to quantum mechanics. And as I was doing this, what ended up happening was I never got to the point at which there was a jump I had to make. I made them look more and more similar, and then they just sort of merged.
I mean, what a feeling that must have been. Was it very exciting, and did it feel like a big aha moment?
No, it was confusing. I thought I had done something wrong. It was actually a moment of complete bemusement and, frankly, a little bit of terror, because I had to teach my class very soon. And I thought, great, now I'm totally confused, and I'm going to show up and I'm not going to know what even to say. So I got very confused for quite a while, not sure what was going on. How did these pictures merge? Like, what's happening here? And what I realized was that I had inadvertently dropped an assumption. I had inadvertently dropped the Markov assumption. And the Markov assumption is just the idea that when describing a physical process, like a Markov chain, like a Markov process, all you need to know is the present state of your system. And then the law will tell you what the next state should be. That's called the Markov assumption. And so with the Markov assumption, you can simply iterate your evolution. You start in the present state, you use the Markov law, it tells you the next state. In the Markov case, for a stochastic process, probabilistically tells you the next state, but for a deterministic process, it would just tell you exactly what the next state is. And once you know the next state, you then apply the law again, and you apply it again. Each time you just take whatever the new present state is and then get the next state, and so you can iterate the steps. And in a Markov chain, you take each step and you sort of iterate them. Usually you discretize time and assume time is comes in discrete amounts. You don't actually have to do that. And I certainly don't assume time is discrete in my work. But in the simple examples, you often take time to be discrete. You go in time steps, and you just apply this iterative map over and over again. You apply this law over and over again, this Markov law. And what I had inadvertently done in bringing these two formalisms together is I had dropped the Markov assumption. There was still probabilities in the laws describing how we get from one state to the next, but I was not assuming that the law should be Markovian, that it should be iterative, that you should be able to iterate it, repeat it, do it repeatedly over and over again to keep getting the next states. When I had dropped that requirement, the theories merged completely and became the same theory. And so it took me a while to figure out that that was what I had dropped. And then when I eventually realized that this was not a Markov process, I started calling it, I guess, a non-Markovian process, but it wasn't quite a traditional non-Markovian process. Traditional non-Markovian processes have what's called memory effects, and you have to impose on the system all of these higher order conditional probabilities, which just retain lots of information about the past. That's not quite what I had. I had a different kind of a thing where there's just a failure to be able to divide up the evolution and iterate it in the normal way. And so I was looking for a word. I thought maybe irreducible processes, but the word irreducible is widely used in mathematics and physics for many things, and I didn't want to do that. So I ended up deciding to call it, well, it doesn't divide in time. I can't divide up the evolution. The laws don't give me the laws at every, from one moment to the next. So I'll call this indivisible. And I did a lot of extensive literature searching, and what I found was that the term was introduced in a 2006 draft article, a so-called preprint article by Mikhail Wolf and Ignacio Chirac in the context of what's called the theory of open quantum channels. They were applying it to a very abstract methodology for studying open quantum systems. They had these maps called quantum channels, which are high-level maps. They act on operators on Hilbert spaces. They're very complicated, but they don't divide over time. This is not quite what I was doing because I wasn't already assuming a Hilbert space picture, but they used this word indivisible, and then I basically tracked the history starting from 2006, and it was in a draft article in 2020, which eventually published in Physical Review X in 2021 by Simon Mills and Kevin Modi, two people who work in quantum information. They took this idea of indivisibility and said, well, you could have a classical stochastic process, just ordinary probability, just probabilities with configurations. And you could imagine this process not being divisible in time, and they called it indivisible. They'd used the same word again that had been used by Wolf and Chirac, and that I had stumbled on using. So I did not invent the word. but they don't really talk about indivisible processes. In their paper, it's like a long review article on classical and quantum stochastic processes. It's available. It's not behind a paywall. People can go and just download the paper for free. It's open access, as they would say. So you can go Google Mills, M-I-L-Z, and Modi, M-O-D-I, and quantum classical stochastic processes. You can read it yourself. And in figure 6 of their paper, they just mentioned you could have a process that is indivisible. They write down the exact same equation I was writing down, even with the same symbols, which is kind of amazing. They use capital Greek letter gamma, just like I was using it. But they say nothing more about indivisible processes. They just mention it as a note that you could have such a process. They don't describe whether you could use this as a set of laws to give a new way to do quantum mechanics. So I breathed kind of a breath of relief that I had not been scooped, although I was almost scooped. But really the idea of a stochastic process, just an ordinary old probabilistic stochastic process being indivisible, is a couple of years old. And this gives a good reason to think, that why this wasn't done before, why no one noticed this before, because I guess no one had considered you could have such a stochastic process. But really, they're very simple processes. Sometimes the simplest things are things that we tend to step over without realizing they're there. And that's the story of how I arrived at this picture. So now we have laws, these stochastic laws, they're indivisible, and they're very simple. In fact, it's very easy to go back and forth between the stochastic laws and the Hilbert space representation of those laws. You just take whatever Hilbert space representation you're using and you flip this switch, and now you have the stochastic one, and you can go back and forth between them. I call this correspondence between the two pictures the stochastic quantum correspondence. Yeah. And with these laws, you generate exactly the same predictions for measurement outcomes for their probabilities that you would get from ordinary quantum mechanics. But now there's no wave function. I mean, when you switch over to the Hilbert space side, you can use wave functions to do calculations, and that's often easier. But the wave function is not a physical object that really lives anywhere. Superposition is not a literal fact. Your system is not superposed physically in two different configurations at once. On the stochastic side, the system is always in one and only one configuration at every moment. Superposition is just an artifact of working with the Hilbert space side of this correspondence. And so there's nothing that ever needs to collapse. So there's no measurement problem anymore. You never end up with a superposition. In the Wigner strand thought experiment, Wigner on the inside does the measurement, and in fact does get a definite result, and Wigner on the outside just doesn't know what the result is. And so yes, there's a hidden variable. The hidden variable is what the result was. And that's it. That's the answer. It's, at least according to this interpretive framework.
Well, does it, aren't you, maybe I'm just being maybe you're just very humble, or maybe it's that I don't, or that I'm overestimating how big of a deal that is. But to me, it seems like you're really unifying something that people have talked about for a long time. And of course, a lot of people have been going down this path with you, and there's a long path to go down. But this feels like a more simple explanation for the reality we live in, and for answering all of these quantum questions, and might be the beginning of a very big change in the whole field. Could I be wrong, or why am I overestimating this?
You could be wrong, you could be right. I'm excited about this. I hope I'm getting across. Okay. I do think this is exciting. I mean, it is where I'm spending a lot of my time and attention these days. I've worked on a variety of other topics, the foundations of physics. I'm spending a lot of my time these days thinking about this particular project, because I do think it's promising. It's just that, in philosophy and in science, all results are provisional. They're all tentative. They all await further work, and they could all end up turning out to be wrong, and I don't want to presume more than I can say. I want to be very modest about what I'm saying here. I don't want to claim that this is, you just said Nobel. I'm not going to claim this is Nobel Prize.
Yeah, you're going to win a Nobel Prize. I just said it right there.
But okay, well, you're the first. I guess you're supposed to be the first, I guess. But I'm not claiming that I can now take this and I can solve quantum gravity and I can solve all. I mean, it's a very narrow problem I'm trying to deal with, which is to make quantum theory an honest physical theory about honest physical things happening. And now, we can say that all the gases mixing in the early universe, or galaxies, those are all things really happening. They're happening stochastically, whether there's anyone observing them or not. There's nothing particularly special about measuring devices. They're only one kind of a system. So it resolves the measurement problem and the category problem. Now, other interpretations also claim to be able to solve the measurement problem, and to the extent people have thought about the category problem, also the category problem. But arguably, they don't meet the criteria I laid out: empirical adequacy, explaining the classical limit, getting rid of all the ambiguities, and not depending on an endless list of extra empirical assumptions. Arguably, and this is what I'm arguing, this is the only approach we have right now that does these things. I could be wrong. There could be a better approach that comes along later. So I don't want to presume more than I can, except that I just regard this as an incremental step in what I hope is the right direction.
Well, they're also just seeing, I mean, I'm not sure how deep in kind of the AI field you are, but the idea that we have these stochastic processes built into neural networks to make these diffusion models seems really interesting. The fact that we have these, trillion parameter models where you can think about the degrees of freedom between all of the nodes and how they kind of exponentially blow up, but there's patterns in there seems like a very interesting thing. And it just feels really fascinating to listen to a podcast like yours and when I'm normally thinking about technology and see so many overlaps. So I'm really excited to see like what the future kind of might discover about both of those systems and if there's some universal laws or patterns that we come across.
I mean, this is the hope for unification between fields, right? I mean, when a new physical picture or interpretation of theory comes about, often it creates bridges or links to other areas that might otherwise have seemed conceptually categorically different. So, for a long time, I think the attitude was that the theory of stochastic processes was just a completely different theory from the theory of quantum theory. They were just different. And what this suggests is that they're actually maybe the same theory. And anything that therefore is phrased in the language of stochastic processes now has a much closer connection to quantum theory. And that means that any intuition that people can bring from these other areas can now be brought to bear on quantum theory, and vice versa. Intuitions we have for quantum theory might have things to say about these other approaches. So, so I think that's great, and it's one of the reasons why I think this work is worthwhile. I mean, one could take the view, look, the ambiguities of textbook quantum theory are so far outside of our technological capacity. Why bother worrying about them? Why even bother? And I think one reason to bother is because, in addition to making the theory honest and self-consistent, sometimes along the way you generate spin-offs. I mean, many very important practical spin-offs have come out of people asking physical, metaphysical, foundational questions about quantum mechanics. Decoherence was arguably discovered by David Bohm in trying to explain the measurement process, which was an absolutely quantum foundations question. And even he, who invented it, in his book, Chapter 22, Section 8, Destruction of Interference in the Process of Measurement, even he realized in talking with Einstein, that it wasn't enough to solve the measurement problem. It's why he introduced his pilot wave theory and his particles. Interestingly, in the acknowledgments of his first paper, the only acknowledgement he has is to Dr. Einstein. He doesn't acknowledge anybody else. And then of course there's more spin-off discoveries. The no signaling theorem, arguably the no cloning theorem, depending on, it was co-discovered by multiple people. But definitely some of them were philosophers of physics, like Dennis Deeks, and then other important results. I mean, EPR states, Bell's theorem, which is now practically used all the time in quantum cryptography and in quantum information. GHZ states, and more. I mean, there are all these spin-offs that have come out of quantum foundations research. So it seems to be quite worthwhile to probe these questions because they sometimes generate new ideas. Yeah.
Feels to me like what you said also gets me imagining a lot of ways we could potentially start testing these kind of theories too, because there's a lot of ways you can architect a system to follow a stochastic process, and we might be able to learn, like, when you set it up a certain way, does that mimic the way that quantum mechanics works in any way, and have some beginnings of evidence for how those two might be explanatory. So
sure, you can imagine creating what are called analog models. An analog model is where you have a physical system that you build using more conventional theory, like a simpler physical theory, more accessible physical theory, that has the same mathematical behavior as a system in the more complicated theory. And so we can use the simpler system in the simpler theory to answer questions or study features of the somewhat less available, more complicated things. So an example would be people using fluid mechanical models of black holes, which have very similar mathematics to Einstein's general relativity, and studying these systems that are mathematically very similar to Einstein's black holes, but we can do them in a lab. We can study them in a laboratory with actual fluids or simulate them on a computer. These are so-called analog models, and there are now analog models you can make for quantum systems. So if you use this sort of stochastic quantum correspondence, you could take a system that is made out of non-quantum physics. I have some simple examples of systems you could build in thermodynamics, but classical type thermodynamics, that have the same mathematical features as a qubit, as the simplest kind of two-state quantum mechanical system. So you can imagine building like macroscopic, like big objects in the lab that you're really using classical physics for, but because they have the same mathematics as these indivisible stochastic processes, then through the stochastic quantum correspondence, they're actually telling you something about the corresponding quantum systems. So these are examples of things you could imagine doing.
How exciting is that? So we might get some answers in our lifetimes to some of these big questions.
Yep.
Is there something that you find yourself constantly trying to unlearn, or that keeps kind of getting in the way of this sort of different way of interpretation? Like, what would you go back in time and kind of unlearn, or maybe not put as deeply into your psyche? That's
a really good question. I find that it's easier and easier to think this way with time, and now I don't often find myself getting stuck that way. But there was a very long time when, like some of the people who attend my talks, even some professors will listen to the whole talk and then they'll say, okay, that's fine, but tell me what happens to the wave function. And I'm like,
that was the whole thing.
Like, that's the whole point, because you get really locked into thinking a certain way, and it's very hard to see outside of that wave function paradigm. And this is what makes paradigms so useful in some ways, because you build all this intuition and you get very efficient at working within the paradigm, but then it becomes very difficult to even conceptualize stepping outside of it. But I find this happens less and less with me. I spent a long time early on very confused what was going on, and now I almost have difficulty understanding why I was so confused, because this picture is in a lot of ways simpler and less abstract. Mm-hmm. I mean, these configuration spaces and indivisible stochastic processes, they don't even have complex numbers in them. I mean, they're super boring. It's like making the world safe for ordinary old-fashioned probability theory again. I find it, if anything, more intuitive now, but I do, when I talk to people, find that they often, a lot of my time is spent, sometimes I give a talk where the whole talk, I don't even get to the main point of the talk, the whole talk is just trying to get them to see more flexibly outside of the way they've been thinking about quantum mechanics.
So I guess with your students now, you can kind of bring some of those concepts in early on and not try to overcomplicate it, just to then bring it back later in their career.
In some ways, I find it much easier to talk to people who are newer to the subject than I do with people who've been working in it a very long time. But, I also know a lot of people who've been working in physics a very long time who have no trouble. I mean, they're very flexible, creative thinkers, and, they make things very easy. I think it's a real difficult balancing act to become very good at thinking intuitively within a paradigm. So you can be very productive and write a lot of really great papers and make very important scientific discoveries, while at the same time maintaining a certain kind of conceptual flexibility. Right? That if the paradigm shifts or there's something that's wrong with the particular paradigm, you don't have much difficulty sort of thinking outside of it. That's a rare gift that I know a few people who have. And I would certainly hope to aspire to have that. But for me, I find it very difficult to shift my thinking. But I know people who find it much easier than I do, and they're
sure.
Great.
And once you've built your career and you're referencing other papers and you've just thought about it, I can see how it's so hard to strip all that stuff down. I mean, that's a problem in many aspects of life.
One of the difficulties in proposing something that's very like a framework shift, not like let's take a current theory and change one thing about it, but like a new framework, is that there are a million questions people have. And you cannot possibly answer all of them in any finite amount of time, even if you know the answers to all of them. So in this conversation, we are only skimming the surface. The papers contain so much information, right, and so many answers to so many questions. But I'll give an interview like this, and I'll maybe look at the comments, or I'll hear people watch it, and they'll say, well, Jacob, it doesn't work because you didn't consider this, and it doesn't work because you didn't consider that. And I'm like, no, I did, but I couldn't possibly get them all into the interview. So let me just quickly say, if you're looking at this and going, well, this can't work because what about Bell's theorem? This can't work because what about remote entanglement swapping? This can't work because it is basis dependent. This can't work because what about interference? This can't work because what about weak measurements? Weak measurements can show wave functions. What about? Just rest assured, I have thought about these things. I don't have time to explain them all right here, but they're in the papers. They're in some of the other talks. And I promise, I've spent a lot of time in this field. I have thought about these things. Don't assume that just because I didn't say one of these things that it's not there. In particular, something like interference is a good example. You can take interference on the Hilbert space side of the correspondence, which shows up as a kind of appearance of cross terms when you calculate things that don't have a clear classical meaning. And these are very mysterious. We don't really have an interpretation for them according to the traditional approach. They're just pieces of mathematics that lead downstream to experimental signatures. But like if someone were to ask you what is interference, what is the meaning of these extra cross terms that show up that don't have a classical meaning, people would maybe say something about waves or something like that. We don't really have a good answer. But there's like a formula you can actually write down where you take the indivisibility property, you take these laws on the stochastic side fundamentally being indivisible, and if you try to split them anyway, if you just demand that they divide, even though they don't, you're going to get the wrong answer. But if you subtract the prediction made correctly with the correct indivisible law, if you take the indivisible law and you subtract from it this by hand division that you've sort of enforced like erroneously, the wrong answer, you could just subtract them. The difference between them is exactly the formula for interference, like down to like the individual terms. So you could just directly see that interference, which had no explanation, is just a manifestation of indivisibility. So, and this is the same thing holds for entanglement and for, like, we didn't even talk about Bell's theorem or local causality, but I have a whole paper on that. It's called New Prospects for a Causally Local Formulation of Quantum Theory. You can go look it up. It's available. It's a preprint draft where I go through and carefully look at the assumptions of Bell's theorem. And there are actually several versions of Bell's theorem because Bell himself couldn't exactly decide on exactly what his definition would be. He kept fishing for one that would be just right, but they all make lots of assumptions, these extra assumptions, and he wasn't happy like all the way to the end. And arguably, he never found a definition of local causality that really means what we want local causality to mean. I guess the last thing is, and this is kind of important, I guess, if someone's watching this and wants to know how to make an impact on fundamental physics, the track record of spin-off discoveries coming out of quantum foundations, I've listed many of them in this conversation, all the way from decoherence to Bell's theorem to GHZ states, EPR states, the no signaling theorem, the no cloning theorem, among many other important results. Even quantum computing, arguably. I mean, David Deutsch's early work in quantum computing, he made very clear in the papers that he was motivated by trying to show that many worlds had to be correct, because in his view, if quantum computers could work and could make and could do things more efficiently than classical computers, it would prove to everybody that it could only be true if many worlds was right. That was his motivation. So you could argue that a tremendous amount of spin-offs have come out of this field, and yet this field, quantum foundations, in particular philosophical physics and the philosophical side of quantum foundations, you could argue that the ratio of people working and money available to the output of this field is extremely small, right? Like very, very few people. I guess the ratio, small or large. Let's say the denominator is number of people, amount of money, and the output in the spin-offs is the numerator. This is a huge ratio. And so if you're, and arguably many people trying to work in this field have struggled to get jobs. Historically, so if you were looking for if anyone's listening to this and they have financial resources and want to know where to devote their money and don't want to give another $1 million to an already very well-resourced field, which might only have, a very marginal utility for that field.
Yeah.
They want to know where their money would make a huge difference. Providing grants and funding and endowed professorships and creating centers and institutes at good universities would be an incredibly effective way to spur interest in the field and potentially have an excellent cost-benefit ratio.
That is crazy too, because we're like looking at the world of infinite money when it comes to AI and servers and everything. It is surprising when you think about this potential overlap. I mean, especially this kind of new and kind of this different way to think about the benefits and what the R&D output could be. So
right.
Yeah, I definitely could. I would love to see a lot more money come into this space also. So. Okay, so you have jacobbarandes.com is a great place to just start the story of what you're up to. You have links there that go to different talks, to different papers, and all sorts of other contact information. But of course, on YouTube, there is a ton of videos to look at, and I will reference many, many things in the description below, so play around in there too.
Thank you. Thank you for this lovely invitation and this opportunity to talk with you today. I hope you had a good time. I hope people watching this have had a good time listening. And, if you'd be interested, I'd be happy to do this again. So let me know.
I know you just sometimes film these things, especially with your Theory of Everything podcast, and you probably just go about your day. But, take a second to realize, like, there at least are a number of people in my world that have just found what you've done extremely fascinating, and it's kind of changed the way they're thinking. And, it's out there, and it's starting to gain momentum. So I'm really excited to see, like, what happens with your career.
That's incredibly kind and generous of you to say. I really appreciate that. It means a lot to hear that, because it does in some ways feel kind of like when you're on stage looking out into, the dark void. The lights are on you. You can't see the audience. You have no idea if there's anyone there at all. What I would say is, look, I've gotten a couple. So, occasionally I get emails from people saying, I've got my own fantastic theory. Please read all my papers. And I get a lot of those, often from people who don't have any background at all in physics. And what I'll just say is, like, please do some studying first, then come back to me. But occasionally I will get a message from someone who just says, I think what you're working on is really interesting. Thank you. And those, like, little notes like that, they mean a lot.
And ideas like this, sometimes they just keep gaining momentum. They're a small snowball that, like, rolls and rolls and rolls. And I don't know. I hope that happens. Or at least we learn something. I mean, that's the way science works. So
my hope is that if this doesn't work out, like you said, at least we'll hopefully learn something, right? Like, either it will work out and that's great, or it won't, and then in showing why it doesn't work, we'll learn something new. My hope is that if it doesn't work, it won't be for some trivial reason.